I was watching a game the other day, staring at that camera gliding over the field on 4 cables, and had a thought. That would make an awesome International Space Station tracker if the model just flew right above the map. So I built one. The very first goal was to make the stepper work, and I was trying to make sure I'm not burning anything. And this is what happened. Wow. This thing is extremely hot. To the point I'm going to question if everything is alright actually here. At that moment I was able to smell the burned plastic, and I had concerns if I actually burn my computer as well. And here's how I got to this point. For the brain I picked an ESP32 and flashed MicroPython onto it. The toolchain is just nicer to work with. First thing I built with codecs was a simple blinker, and used my multimeter as a canary to confirm a pin was actually going high and low. That worked just fine. The next step was making the stepper motor rotate. Just rotate, nothing fancy yet. I connected 4 control wires to the motor driver and set up 2 power sources. A USB battery for the motor itself and my computer powering the ESP32. 2 separate power sources means they need a common ground, so I bridge the ground from the USB plug to a ground pin on the ESP32. And then I created a program with the codecs which simply rotates the motor. Started the program, nothing happened. I started changing wires, wiggling connectors, looking for anything loose, and then I noticed a smell, burned plastic, and the driver was way too hot to touch. So I immediately turned everything down and investigated for a while. Turned out I had the battery connected with the polarity reversed. Positive into the driver's ground. Classic mistake. I swapped the wires, let everything cool down, and started the program again. The motor turned, and somehow neither the driver nor my computer took any damage. I guess I got lucky. I tested how precise the stepper motors actually are and discovered they drift a lot. The whole project depends on one assumption, that the motors are precise. This is an open loop system. There are no sensors telling me where the model actually is on the board. The software tracks position by counting steps, so if there is a misstep, then error accumulates forever. So I attached one of stepper motors to a frame from another project and wrote a simple test. Rotate 2 full turns one way, then 2 full turns back, and it should land in exactly the same position every single time. It did not. I start playing with the delay in between steps, too fast and the motor skips steps. The coils don't have enough time to fully energize before the next step fires. I found that 3 milliseconds was the edge of reliable, so I set it to 4 to give myself some margin. And after that, 2 turns out, 2 turns back, same position every single time. With the stepper figured out, I thought the rest would be a piece of cake. I designed elements in FreeCAD. First was the motor frame, a square board with 4 slots for the motors and 4 slots for drivers sitting next to them. Everything in one piece, so no wires were running across the mat to separate boards. That was very clean. Then the 4 towers, one for each corner, to route the cables down the ISS model. Those I printed in pieces and glued together, mostly because I kept having to adjust the cable holes, and the printing a full tower every time was 4-hour commitment I didn't want to make. For the base I needed something flat and rigid to mount everything on and put the continents for the map. I didn't want to waste material printing a large board, so I grabbed the mat I had laying around and used that instead. Both the motor frame and all 4 towers have slots on the bottom that clip directly onto the mat, so there is no screws, no glue, maybe a little bit of electric tape. Then I assembled everything together, and for the first time the whole thing looked like an actual project rather than a pile of parts. With the frame assembled, I added jumper wires to each motor driver, and then came the cables. I used regular sewing thread, not ideal, but that's what I had around. The first problem I hit was getting the thread onto the spools. I started winding manually and gave up after about 30 seconds. So I asked Codex to write me a program to rotate all 4 spools simultaneously, and all I had to do is keep slight tension on the thread with my fingers while it wound itself on. That worked. With the cables ready, I needed something to hang in the middle. I had a 3D printed ISS model, but at its scale it looked pretty ugly, and more importantly it was too light, not enough weight to keep the cables under tension. So I attached the cable to a USB plug instead, better looking and actually heavy enough to work. Practical beats pretty. Then I wrote the first real movement code. The coding system is simple. The board is 450 by 300 mm, so the center is 225 by 150. Given any XY position in millimeters, the code calculates how long each of the 4 cables needs to be and drives the motors to match, and tries to drive all the cables' length proportionally to number of steps needed. I tested horizontal mode first and then vertical. Both worked just fine. With the mechanics working, or so I thought at the moment, it was time to make the thing actually look like a map. I found a 3D printable continent set online, links in the description, printed them out and laid them on the board. But placing them correctly is not as simple as eyeballing it. Every continent needs to land in exactly the right position. So I wrote a small application, then converts real GPS coordinates into XY millimeters on the board. Here, for example, is the tip of South America. These are its GPS coordinates, and the app translates that to this exact point on the board. Place the continent so that the points are lined up, and the whole map snaps into the right position. This was supposed to be the resounding success moment. I moved the model to the live location of the ISS, and it crashed into the ground. Here is how I got to this point. I asked Codex to write the code to connect the ESP32 to my Wi-Fi, pull the current ISS coordinates from the internet, and convert them into a position on the board. The test plan was simple. Move the model to the location of the ISS, wait a few seconds, and return back to 00, which is just off the left coast of Africa. So round trip was there to prove if everything works end to end. One thing worth explaining here, the model always starts from a known location. Every move is calculated relative to where the model currently is, because that's what keeps the cable length accurate. There is no sensors and no cameras, just the math and trust that the previous move landed correctly. So I checked the ISS location on iPad, started the program, and watched the model move. It was going roughly in the right direction, until it just hit the board. So something obviously was wrong, and the question was what. I did a few more runs to make sure the problem is actually repeatable, and it does. And then I switched to test non-coordinates. I would move the model to the left and back and bottom and up. And that, to my surprise, worked just fine. So it was the time to go into source code and try to review it. I did give a try to Gemini and Claude. I was not able to find any reasonable solutions from them. They had a few ideas here and there, but none of them were actually useful or applicable in my case. So I had to see what I can do better. So I tried probably 10 different fixes and various ideas, but the model were not able to keep a consistent height no matter what. So I decided to take a couple of days off from this project to think about this. What you see here now is the result after a few days of debugging. I decided to refactor the motor management code completely and work through it step by step with Codex instead of feeding one large prompt. The first change was switching from tracking cable length to tracking steps directly, under the assumption that steps are not being skipped. I verified that assumption for each motor and each tower individually. All good. Then I tackled the movement itself. As a first pass, instead of moving all 4 motors simultaneously, I moved them once at a time sequentially, just to isolate any issues. If something goes wrong, I know exactly which motor caused it. Sequential motor worked, but the model moved with a lot of shaking. No surprising, just confirming that mechanics were sound. Next, I asked codecs to move all 4 motors at the same time. Same altitude problem as before, the model was dropping, but now at least I know that it's deleted. So I knew the sequential version worked, so the bug was specifically in the simultaneous movement logic. So I asked codecs to implement a tick-based algorithm. Every tick accumulates fractional steps for each motor, and fire a step the moment the accumulation crosses a whole number. All 4 motors coordinated through the same clock, and that just worked. With everything working, I put it on a loop to ping the ISS every 30 seconds and update the model position automatically. Because the ISS takes 92 minutes to complete a full orbit, the movement of this map is pretty slow in real time, so I've sped this footage up. But if you walk away and come back an hour later, it's halfway across the planet. For a Saturday afternoon project, it's a pretty good result. Version 2 will track the ISS all the way down when NASA deorbits it into the Pacific around 2030. Stay tuned for that.